Okay, so let's start. Welcome to week 12's problem solving session. Today we'll solve some problems related to week 12's assignment. Uh, is my screen visible? Am I audible?
Yes, sir. Yes, sir.
Yeah. Okay, since these problems are based on the assignment that you just solved, you might know the answers, and in that case, you can put the answers in the chat. Okay, so let's start. So the first problem is select the correct options. Option A is in additive secret sharing. Every party gets n minus 1 shares. Option B is as a part of any secret sharing mechanism, it is possible to reconstruct the secret only when all parties come together. Option C is additive secret sharing needs order and random numbers, and replicated secret sharing requires n to the order t random numbers. So over here by replicated secret sharing, I just mean that we want to accomplish n comma 2 secret sharing. And in order to do that, what we are doing is we are just repeating like additive secret sharing multiple times. So that's what I mean by replicate secret sharing. So replicate secret sharing is just the way of achieving n comma t secret sharing using additive secret sharing scheme that we already saw in class. And option D is additive secret sharing needs n to the order t random numbers, and replicated secret sharing requires order n random numbers. So which of these options are correct? Okay, the correct answer is the correct answer is C. And okay, so before I show you why C is correct, let's cover all the options and see why all the others are incorrect. So in option A, we have in additive secret sharing, every party gets n minus one share. Well, this is incorrect because every party just gets one share. Option B is as a part of any secret sharing mechanism, it is possible to reconstruct the secret only when all parties come together. This is only true if we have n comma n minus 1 secret sharing. However, if we have n comma t secret sharing where t is strictly less than n minus 1, then as long as t parties come together, that we can reconstruct the secret. And since t is strictly less than n minus 1, t plus 1 is strictly less than n. So if we want to do n comma t secret sharing, where t is strictly less than n minus 1, then we should be able to reconstruct the secret even though fewer than n parties come together. So B is also incorrect. About option D, additive secret sharing scheme requires n to the order t random numbers, and repeated secret sharing requires order n random numbers. Well, if option C is true, then replicated secret sharing requires n to the order t random numbers, which is more than order n to the t, right? Sorry, order n. So if option C is true, option D can't be true. In particular, if this part of option C is true, then this part of option D can't be true. So we have seen that A and B are false, and that D is false if C is true. So now let's see why C is true. So in the editor, so in the additive secret sharing scheme, the dealer picks n uh, n minus one random numbers. Let me call these S1 to Sn minus 1 and shares these numbers as the secret shares of the parties. Uh, P1 to Pn minus 1. Then it computes Sn defined as and shares Sn with Pn as its secret share. So there are n minus 1 random numbers, or rather, let me. So there are n minus 1, which is order n random numbers, uh, S1 to Sn minus 1 in the additive secret sharing scheme. Yeah, so over here S1 to Sn minus 1 are random and Sn is not random. So there are n minus 1 many random numbers and n minus 1 is order n. So the first part of option C, which says that additive secret sharing needs order n random numbers, is true. Yeah. So now let's see why the second part, that is replicated secret sharing requires n to the order t random numbers, is also true. So secret sharing are done using replicated secret sharing scheme. The dealer executes t plus 1 comma t editor secret sharing. Yes. If you have a question, you can directly ask in the chat. Uh, or you can unmute yourself and ask as well. So Mohan, do you have a question? So Mohan, I see you have raised your hand. Do you have a question? Okay, so in case you have a question, you can put it in the chat. I'll yeah, continue with this question. Yeah. So in n comma t secret sharing done using replicated secret sharing scheme, the dealer D executes t plus 1 comma t additive secret sharing with every subset of parties P1 to Pn of size T plus 1. Right. So the total number of instances of the editor secret sharing scheme is equal to the number of subsets of n. So by this notation, I mean the set 1 to n. Yeah, so the number of two instances of the additive secret sharing scheme is exactly equal to the number of subsets of n of size t plus 1, right? And this is equals to n choose t plus 1. Let me add a page. And this is just n times n minus 1 all the way to n minus t minus plus. mm, n minus 1 t divided by t plus 1 factorial. So now notice that in the numerator there are t plus 1 terms because the first term is n minus 0, second is n minus 1, and the last is n minus t. So from 0 to t there are t plus 1 terms. So I can upper bound the numerator, and each and every term is at most n, right? So I can upper bound the numerator by this. Um, this let me keep as it is. So this is the total number of instances of additive secret sharing scheme that are executed, right? Now, per instance of the t plus 1 comma t additive secret sharing scheme, we need so over here while looking at over here while trying to answer the first part of option C, we saw that if we do secret sharing with n parties, that is if we do n comma n minus 1 secret sharing, then we need order and randomness, right? Over here we are doing multiple instances of t plus 1 comma the additive secret sharing, so we need order t plus 1 random bits, right? So total number of random bits of random numbers.
Sir, any previous year question papers is there for external exam preparation purpose?
So I don't have any question papers. So unless the instructor uploads it on the NPTEL site, I don't think there are any papers.
Okay, sir.
Yeah. Right, oh yeah. So the total number of random numbers is equal to the number of instances of t plus 1 comma t secret sharing times uh, random numbers per instance. And this is just, okay, not equals to. This is upper bounded by n to the t plus 1 over t plus 1 factorial times order t plus. So now I want to upper bound this again. Now notice that order t plus 1 is much less than t plus 1 factorial. So uh, what I can do is this. I can upper bound order t plus 1 by t plus 1 factorial. And this is just n to the t plus 1, which is n to the order t. Yeah. So so in repeated secret sharing, we require n to the order t many
Sir,
random numbers.
because of my busy schedule, I did not attend the live classes, sir. Sir, how can you pass the exam, sir?
So,
Any material?
so are you talking about these problem solving sessions?
What, sir?
Like, are you asking about? So, did you? What are you saying exactly? Are you saying that you did not attend the problem solving sessions, or did
No,
not
sir.
see the lectures?
Yes, sir. Yes, sir.
Okay, so okay, what I'm asking is, did you not attend the problem solving sessions, or did you not see the lectures?
Lecture, sir.
Oh, so okay, so but if you are, I think I don't. Okay, so there are some books that you can read if you don't want to attend the lectures, but I think since the course content and the syllabus is from the lectures, I don't see how you would be able to learn the material without seeing the lectures.
Okay, sir.
Yeah.
Bro, I have wrote exam, any exam about the cryptography.
So I couldn't like get your question. Can you please repeat it?
I have wrote the exam, cryptography, previous year or previous exam.
Like, can you please write it in the chat because I still don't clearly hear the first part of your question.
Yeah, bro, he is asking that have you attended any previous year exams, cryptography NPTEL exam?
Oh no, no, no. I haven't done cryptography in NPTEL.
Okay.
Yeah. Okay, so if there are no other questions, let's continue with this. So yeah, when you have so when we want to do n comma t secret sharing using replicated secret sharing, we need n to the order t random bits, which is yeah the second part of option C. So yeah, both parts of option C are correct, and so option C is correct. And as we saw, that implies that option D is wrong. Yeah. So the only correct option is C. Is this fine? Okay, so if this is fine, then let's move on to the next problem. So the next problem is for the equation 17x is equal to 1 mod 27, which of the following is or are true for x? Option A is there exists no solutions. Option B is there is more than one solution for x in Z27. That is the group. It is a group of numbers with the operation being addition mod 27. Option C is there are finitely many solutions for x in Z. And option D is there are infinitely many solutions for x in Z. So which of these are correct? Okay, so let's go over this option by option. In the first option, we have that there exist no solutions. Well, this is false because so we have 17x is equal to 1 mod 27 as rather let me write it like this. Since 17 uh, is e is co-prime to 27. Uh, the inverse of 17 mod 27 exists. That is, there exists A in uh, Z27 cross such that uh, 27 such that A times 27 is equal to 1 mod 27, right? There. So 17 uh, x equals to 1 mod 27 implies that I can multiply A on both sides. And now 17A is equal to 1 mod 27, right? So we get that x equals to A mod 27. So A is a solution for the equation, right? Okay, so A is in Z27 cross. So A is in Z27 cross, which is subset of Z27 is the solution. Hmm. Yeah, so option A, which says that there exists no solution, is false. What about option B? There should be out. Yeah. So option B is there are more than one solutions. This should be solutions. So there are more than one solutions for X in Z27. Okay, so this is also false, and let's see why. Okay, so if 17x equals to 1 mod 27, that is 17x minus 1 is equal to 0 mod 27. That is 17x minus 1 is divisible by 27. Then 17x minus 1 is also divisible by 9 because 9 divides 27, right? So 17x minus 1 equals to 0 mod 9. But since now I'm doing uh, arithmetic mod 9, I can also reduce 17 mod 9. And 17 mod 9 is just minus 1. Because 17 is 18 minus 1, right? So this implies that x minus x minus 1 is equal to 0 mod 9. Which implies that x equals to minus 1 mod 9. Now, okay, so now we are in option B, we are interested in the solution number of solutions in Z27, right? So what we can do is the following. So, okay, rather let me not write this part. Okay, so we have minus x minus 1 equals to 0 mod 9. And this implies that x minus x minus 1 is equals to m times 9 for some m less than 0. Or rather, let me for some, yeah. So now, okay, minus x minus 1 is always going to be a negative number. So if minus x minus 1 is divisible by 9, it would look like m times 9 for some negative integer m, right? Okay. So now let's see how many of such numbers exist in Z27. Okay. So if m equals to 1, sorry, m equals to minus 1, we get minus x minus 1 equals to minus 9, which implies x equals to 8. If m equals to minus 2, we get minus x minus 1 equals to minus 18, which implies x is equal to 17. And if m equals to minus 3, we get minus x minus 1 equals to minus 27, which implies x is equal to 26. Now for m equals to minus 4, we would get a number larger than 27, right? So that number won't be in Z27. So the only three solutions in Z27 are 8, 7, and 16. 26. Now, as we saw before, if 17x equals to 1 mod 27, then 17x must also be equal to 1 mod 9. So, the only possible solutions of 17x equals to 1 mod 9 in Z27 are 8, 17, and 26, right? Okay, so these three are the only possible solutions. However, not all of these need satisfy the equation, right? These are just possibilities. These are just candidates. So now let's see how many of these are solutions. Okay. So if we can show that exactly one of these is a solution, then we would have shown that 17x equals to 1 mod 27 can have only one Okay, solution is Z27, right? And that would show that B is false, which we want to do. So now let's show that only one of these is a solution. So for x equals to 8, 70x is equal to, okay, 17x minus 1 is equal to, yeah, let's, this 17 8 minus 1 is equal to this. 1780 minus 1 is equal to 135. And when I do mod 27, so when I divide 135 by 27, I get an integer, which means 137 is divisible by 27. That is 130, sorry, that is 135 is divisible mod 20, divisible by 27, and that is 135 is 0 mod 27, right? So this is 135 is equal to 0 mod 27. So x is equal to 8 is a solution. What about x equals to 17? 17x minus 1 is equal to, so it's 288. And 288 is not, so when I divide 288 by 27, I do not get an integer. So 288 is not divisible by 27, and 28, therefore 288 is not 0 mod 27. So x is equal to 17 is not a solution. What about uh, x is equal to 26? Yeah, let's do 17 times 26 minus 1. So it's 441. And this is also not 0 mod 27 because this is not an integer. Yeah. So the only solution is 8. Yeah. So option B is also false. There are not there's only one solution in uh, set 27. Now, since this is a degree 1 polynomial, you might be tempted to say immediately that this has only one solution in Z27. However, the statement that a degree D polynomial is at most D roots is only true over a field, and Z27 is not a field because 27 is not a prime number. So we can't directly use the fact that a degree 1 polynomial has only one root to argue. We cannot directly use that fact over Z27. So yeah, we need this lengthy argument to show that there exists just one solution of the equation mod 20 in Z27. So B is also false. What about C? There are finitely many solutions of X in Z. So C and D are are negations of each other, right? So C says that there are finitely many solutions of X in Z, and D says there are infinitely many solutions of X in Z. So what we will show is that D is true, and therefore C has to be false. Okay, why am I getting this? Yeah. So we'll show that D is true. That would imply that C is false. Let's see why D is true. So let so 8 is the solution of 17x equals to 1 mod 27. So for all integers n, Uh, 27m plus 8 is also a solution as 17 times 27m plus 8 equals to 17m times 27 plus 17 times 8. Now, since we have this 27 over here, this is 0 mod 27, and we've already seen that 17 times 8 equals 1 mod 27, right? So is equal to 0 plus 1 mod 27 is equal to 1 mod 27. So for every integer m, 27m plus 8 is also a solution of the equation. So there are infinitely many solutions because there are infinitely many values of m. So option D is correct, and so option C is false. Is this fine? Yes, if this is fine, then let's move on to the next problem. Yes, so the next problem is which of the following statements is or are incorrect for zero knowledge proof systems? The options are one round of interaction between the prover and the verifier is not enough to convince that the verifier to not enough to convince the verifier that the prover is correct. Option B is a passively secure protocol can be converted to a protocol that is secure against active adversaries using zero knowledge proof systems. Option C is a corrupt prover has zero success probability in each round. And option D is with respect to the completeness property, some rounds will not be successful. So which of these are correct? Let me turn on the light. That's better. Okay, so let's go over all the options. Option A is one round of interaction between the prover and the verifier is not enough to convince the verifier that the prover is correct. Well, this is true because if there is only one round of interaction, then only the prover can send a message to the verifier. But the prover can't send the entire, so only the prover can send a message to the verifier. So if using just this message, the prover wants to convince the verifier, then this has to be a proof, right? But the prover does not want to reveal the proof or the witness because this is zero knowledge, right? So yeah, using just one round of interaction, the prover cannot convince the verifier that the statement is correct if you want to do this in zero knowledge fashion. So option A is correct. What about option B? A passively secure protocol can be converted to a protocol that is secure against active adversaries using zero knowledge proof systems. This is true, and we saw this in class, right? So this is one of the motivations for studying zero knowledge proof systems. So B is also true. B is also true, and so yeah, it's not an incorrect option. Now about option C, a corrupt prover has zero success probability in each round. Well, this is false because we know that a corrupt prover would not succeed in convincing the verifier at the end of the protocol, right? But there are multiple communication rounds in the protocol, and in some of these rounds, the corrupt prover might succeed. It's just that it won't succeed in all the rounds together. So option C is false. So option, and therefore we should pick it because the question asks us to pick incorrect options. And what about option D? With respect to the completeness property, some rounds will not be successful. So this is also false because the completeness property says that the, at the end of the protocol, the verifier would be convinced that the prover, the prover, the, the verifier would be convinced that the statement is true, right? And for that, it has to be for that each and every round, individual round must be successful. So option D is also false. So yeah, A and B are true, and therefore we should not pick those options, and C and D are false, therefore we should pick those options. So now let's look at option or question 4. The question is choose the incorrect options from the following, and the options are A. In an n comma t additive secret sharing scheme, T denotes the number of correct parties. Option B is the n comma t secret sharing scheme consists of three phases, namely the sharing phase, the opening phase, and the reconstruction phase. Option C is the n comma n minus 1 secret sharing scheme will not guarantee the correctness property as there is only one honest party. Option D is none of the above. So let's go over all these options one by one. In option A, we have in an n comma t additive secret sharing scheme, T denotes the number of correct parties. Well, this is true because in an n comma t additive secret sharing scheme, we want to ensure that the secret can only be opened if there are t plus one parties. And yeah, so even if t parties are corrupt, we are fine. So yeah, option A is true, and therefore we should not pick it because we have to pick incorrect options. What about option B? The n comma t secret sharing scheme consists of three phases: the sharing phase, the opening phase, and the reconstruction phase. Well, this is false because there are just two phases. First, the dealer shares the secret shares, and then whenever the parties want to uh, open the secret, they T plus one many of them come together and reconstruct the secret. So there are just two phases: the sharing phase and the reconstruction phase. There is no opening phase. So B is false, and therefore we should pick B. What about option C? The n comma n minus 1 secret sharing scheme will not guarantee the correctness property as there is only one honest party. Well, this is also false because so recall what the correctness property is. The correctness property says the following. Okay, let me write it. So this is what the correctness property says. So for an n comma n minus 1 secret sharing scheme, all the correctness property says that if all the parties come together, they should be able to open the secret, which will happen, right? So yeah, option C is false. That in because in an n comma n minus 1 secret sharing scheme, the correctness property is guaranteed, even though there is just one honest party. So both B and C are false. So D cannot be false because none of the above are false. Is not true. So B and C are false, and yeah, A is true. Now let's look at problem 5. So in this problem, we are asked that suppose that the staff of a bank consists of three clerks and two managers. The key to the bank's treasure room is an L-bit number. The following combinations should be able to open the safe or the treasure room. And the combinations are all three clerks together and number two, both managers together. So which of the following are true for the secret sharing of the key? And the options are: one instance of additive secret sharing cannot solve the problem. Option B is one instance of Shamir's secret sharing cannot solve the problem. Option C is there is no way to secret share a key satisfying the above conditions such that each party ends up with a single L bit share. And option D is it is possible to solve this problem such that two clerks and a manager cannot open the treasury. So now let's go over all these options and see which of these are true. Okay, so first let's see why option A is false. So if we use then all five parties. So recall that in the additive secret sharing scheme, we would, so if we execute the additive secret sharing scheme with five parties, it would be a 5, 4 secret sharing scheme. So all five parties would be required to open the treasury room, right? Which is not what we want. Or rather, let me, all five parties would be required to reconstruct the key. Yeah, so in this case, just three clerks or two managers won't be able to reconstruct the key and therefore won't be able to open the safe, right? So A is false. What about B? One instance of Samir secret sharing cannot solve the problem. Okay. Yeah, so one instance of editor secret sharing cannot solve the problem, so A is true. What about B? One instance of Shamir secret sharing cannot solve the problem. A is yeah. So if we use n comma t Samir secret sharing scheme, then it is possible that t plus one parties can come together to reconstruct the key and therefore open the safe. However, in this t plus one parties, we can have some clerks and some managers, but we do not want some managers and clerks to collude to open the safe, right? We only want that three clerks should be able to open or two managers should be able to open. So we cannot solve this problem by using just one instead of Shamir secret sharing scheme. So this is also. What about C? There is no way to secret share a key satisfying the above conditions. so that each party ends up with a single L bit share. Well, this is false. And so what we'll do is we'll see that option D is true. And to prove that option D is true, we'll come up with a scheme in which each party needs just a single L bit share. So in the proof of the fact that option D is true would imply that C is false. So let's show that D is true and in the process show that C is false. Okay, so option D is it is possible to solve this problem that two clerks and a manager cannot open the treasury room. So here's how we can solve it. The three clerks and use 2 comma 1 editor secret sharing. Right. So if we do this, first of all, notice that every clerk and every manager just gets one share. So this scheme satisfies the property given in C. So if we can show that this scheme works, then C would be false. So now let's see why this scheme works. So since we are using 3 comma 2 additive secret sharing scheme for clerks, any two clerks cannot open the safe, but all three of them together can open the safe, satisfying this condition. And we are also using 2 comma 1 additive secret sharing scheme for managers. So so both managers together can open the safe, but any one manager cannot open the safe on their own. So both these are satisfied. And what about two clerks and a manager colluding to open a safe? Well, since we have used two different instances of additive secret sharing schemes for clerks and managers, two clerks and a manager cannot collude to open the safe because their shares are not compatible with each other. So their shares together won't give you any secret. Yeah, so option D is true. This scheme basically works. So yeah, A, B, and D are true. So now let's look at next problem. So the next two problems are about, so in the class we saw a zero knowledge protocol for graph isomorphism or GI. The next two problems propose variants of that protocol we are and we want to see if these variants are zero knowledge or not. So the problem is consider the following variant of the zero knowledge protocol for GI. The verifier picks a random bit from 0, comma 1, computes a random permutation H of GB, and sends H, comma B to the prover. The prover sends a sigma such that H equals to sigma of GB bar. The question is this protocol zero knowledge? Okay, so the answer is no. Let's see why. So protocol is as follows, right? You have prover, you have verified. So I'm assuming that the G1 and G0 and G1 are n. So the number of vertices in G0 and G1 is equal to n, and Sn is just the set of all permutations on the set of the set 1 to n. Okay. So this is exactly what's done in the protocol. P sends sigma and P checks if okay. So let's see if this is the protocol. Now let's see if this is zero knowledge or not. Okay. So now we have that H, then rather okay, let me write like this. Suppose the verifier accepts, then we have H is equal to sigma, but we also know that H is equal to phi GB, right? So we have phi, which implies that GB. Yeah, so GB equals to phi inverse of sigma of GB, right? So sigma is an isomorphism. Well, let me write this. Yeah, so sigma inverse phi, sorry. So phi inverse sigma is an isomorphism that maps G1, G2, GB to GB bar, right? And since the verifier knows phi, and since the verifier also knows sigma, the verifier can easily compute phi inverse sigma. And so the verifier does, after this protocol has been executed, the verifier does find out a permutation or an isomorphism that maps GB to GB bar. And so this protocol is not zero knowledge. Yeah, so the protocol is not zero knowledge. And what about option question 7? This is another variant of the zero knowledge protocol. Consider the following variant of the zero knowledge protocol for GI. Now the prover picks a bit uniformly at random from 0, 1, computes a random permutation H of GB and sends B, H, psi to the verifier. Yeah, psi is some permutation. The verifier accepts if and only if H equals to psi of GB bar. The question is this protocol zero knowledge? It turns out even this protocol is not zero knowledge. So recall that for a protocol to be zero knowledge, three things have to be satisfied. Number one, it should be complete. Number two, it should be sound. And number three, it should have the zero knowledge property, right? So this protocol over here is not sound. Let's see path. So here's the protocol, your approval. Okay, now, so this is the protocol. Now, what can happen is the following. A cheating prover. So suppose that G1 is not isomorphic to G2. Consider so instead of computing HS5G, it computes HS5G bar. And since uh, so what check does the verifier perform? So verifier checks if shy GB bar equals to H. So in this case, shy is 5, right? So since shy, which by definition is H, yeah. So the verifier, even if G1 and G2 are not isomorphic, the verifier, a cheating prover can make the verifier acceptance property 1. And this violates the soundness property, right? So yeah, the soundness fails, and so this protocol is also not zero knowledge. Also not a a valid zero knowledge protocol because a valid zero knowledge protocol must have completeness, soundness, and zero knowledge, all three properties. So both the protocols proposed in question 6 and 7 are not zero knowledge. Now let's look at the eighth problem. Eighth problem is let n be a natural number. Use Bezos' theorem to prove that Zn cross is the set A in n so that A and n are coparent. So let's see how to do this. So Okay. Okay, one. That is for every b in Zn minus g, there is no multiplicative inverse mod n. And claim 2. No, rather, let me call it d. Already using b over here. That is for every a in g, there exists a multiplicative inverse mod n. So this will show us that the only numbers which have multiplicative inverses mod n are the numbers in G. Then it's easy to show that this is also closed under multiplication and has the identity of element. So yeah, if we prove claim 1 and 2, we would have shown the you know, this. We have shown this. So let's prove both these claims. Suppose for a second. Now LCM of p comma n is a common multiple of both p and n. So it is obviously divisible by n. This implies that because the LCM of B and N is exactly this. Since okay, so yeah, we can this. Now we are assuming that there exists a C such that BC equals to 1 mod N. So what I can do is let me multiply C on both sides. So I get B times C. But B times C equals 1 mod N. So this implies Now, since P is in Zn minus G, the numbers in G are all the numbers which are co-prime to N. So so any number in Zn minus G is not co-prime to N. So B and N are not co-prime. Yeah, so assuming that there exists a secret that BC equals to 1 mod and leads us to a contradiction. So we are forced to conclude that there does not exist any C such that BC equals to 1 mod n. So that proves claim 1. About claim 2, okay, so yeah, okay, before we play through claim 2, let's recall Bezo's theorem. Yeah, so this is what Bezo's theorem says. So because the GCD of A and N is 1. So this implies now N is divisible mod N. So this, when I go mod N on both sides, I get. So if I take D equals to S, I get a D, so that AD equals to 1 mod N. I still need to show that this is in G, right? Rather, okay, let me put it like this. Mod N. Yeah, so then PA equals to SA equals to 1 mod N. Now I need now from okay, D is in ZN. Yeah, so D must be in G. So we have shown that there exists D in G such that, oh, yeah, I should write a D in G. So we have shown that there exists a D in G so that AD equals to 1 mod n. So claim 2 is true. And as we saw before, claim 1 and 2 together would imply that Zn equals G. So yeah, so we have proved that Zn equals G. Now let's look at a couple of questions based on Euclid's algorithm to compute GCD. So the first problem is that prove that Euclid's algorithm computes the GCD of its inputs. So let's first state the algorithm and then prove its correctness. Algorithm is as follows. Yes, so you want to prove that this algorithm outputs the GCD of A and B. And however, in order to do that, we first need to show that this algorithm actually terminates in a finite amount of time, right? First, let's prove that. So even before I do this, we establish some notation. Yeah, so since this is an iterative algorithm, I'll just to differentiate between AIs and B, the value of A and B in different iterations, I'll just call these values AIs and BIs. Okay, so suppose that Then, uh, okay, this. Yeah. So we saw that uh, if A, if for some iteration AI and BI are not the same, then AI plus 1 would be smaller than AI. However, this process of decrease can only go on for a total of A many rounds, because otherwise uh, A would become zero, right? And it's clear from the algorithm that A would never be A would always be greater than equals to zero. So within A steps, we must have an iteration in which AI and BI are the same. But in that case, the remainder R in that iteration would be zero. And so the next B, that is BI plus one, would be zero. And so this check will fail before executing the I plus one I plus one iteration. And so the entire algorithm would stop after I iteration, right? But we saw that I is at most A, and so the algorithm must terminate within A iterations. So the algorithm does terminate. Now, so now that we know that that it terminates, we know that this loop is not an infinite loop. That is, this step is executed. Now what we'll show is that when this step is executed, A is actually the GCD. So towards that, we'll prove this claim. So in the ith iteration, we would have R equals to AI or BI. And this implies that R equals to AI minus M times BI. Because this is what it means for R to be A mod BI, right? Hence, okay, now R is going to be, so if you look, see over here, R is going to be B plus 1, right? Sorry, BI plus 1. So I claim that because of this reason, the GCD of AI and BI divides BI plus 1. Why? Because the GCD of AI and BI is going to divide AI and it's going to divide BI, right? So it's going to divide this entire sum, and therefore it divides BI plus 1. So GCD of AI and BI divides BI plus 1 as AI plus 1 equals to BI. GCD of AI also divides AI plus 1. So now GCD of AI and BI divides BI plus 1. It also divides AI plus 1, right? So it divides both of them. That is, it's a common divisor. So it has, since it is a common divisor of AI and AI plus 1 and BI plus 1, it must divide the greatest common divisor, right? So, or okay, in other words, it must be less than the greatest common divisor. So the GCD of AI plus 1 and BI plus 1 is less, oh sorry, is GCD of AI and BI is less than the GCD of AI plus less than equals to GCD plus 1, BI plus 1. Okay, so what we want to prove is that the GCD of AI and BI is the same as the GCD of AI plus 1 and BI plus 1. So we have showed that this is true. Now what we show is that this is true. And this together would imply that this is true. So BI plus 1 imply that AI is equal to BI plus 1 plus M times AI plus 1. So the GCD of this divides AI. Why? Because the GCD of AI plus 1 and BI plus 1 will divide BI plus 1 and AI plus 1. So it will divide this entire sum, and so it will divide AI. Also, as uh, BI equals to AI plus 1, GCD of also divides BI. So, so the GCD of AI plus 1 and BI plus 1 divides both AI and BI. So it's a common factor of AI and BI, and therefore it must be less than the greatest common factor, right? So we get that So let me call this one. Let me call this 2 from 1 and 2. Yeah, and this is exactly what we wanted to prove, right? So now we have shown that the algorithm terminates and this is true. So as long as we can show that when the algorithm terminates, that is in the last iteration, A is the GCD of AI and BI. So let's say if I is the last iteration and A is the GCD of AI and BI, then we are done. Okay, now let's show that. Such an I must exist because the algorithm terminates. Then AI equals to BI and AI is the GCD of AI and BI from claim 2. This means that AI is the GCD of AI minus 1 comma BI minus 1, which is the same as the GCD of AI minus 2 comma BI minus 2, and so on, all the way up to GCD of A1 comma B1, but A1 and B1 are just A and B. Yeah, so AI is the GCD of A and B. Okay, and now uh, since BI is 0, yeah, so when BI is 0, this check would fail. So this loop won't be executed and will directly go to step 4 and output AI. But AI is the GCD of A and B, and so the algorithm outputs the GCD of A and B. So this proves the correctness of Euclid's algorithm. Now, in claim 1, or rather in the proof of claim 1, we saw that the algorithm terminates with an AI iteration of the while loop. Okay. Uh, what we'll do in the next problem is we'll improve this upper bound. That is, we'll improve an upper bound on the running time of Euclid's algorithm. So let's obtain a better upper bound on the running time of Euclid's algorithm, better than E. So there fix any iteration. Uh, there are two cases. First one is bi is less than ai equal to ai over 2. And since ai plus 1 equals to bi is less than or equals to ai over 2. As ai plus 2 is less than or equals to ai, case 2 is negation of case 1. Okay, so bi is greater than ai over 2. That means that uh, ai mod bi is just ai minus bi, and this is less than or equals to ai minus ai over 2. So bi plus 1 is less than or equals to ai over 2. Uh, ai plus 2 equals to bi plus 1. So again, just as in case 1, ai plus 2 is less than ai over 2. So what cases? So what happens in both cases is that uh, after every two iterations, the value of ai drops by 2, right? So suppose that the algorithm runs for capital T iterations of the while loop. Then what will we get? We'll get that at is less than or equals to at minus 1 over 2 is less than or equals to at minus 4 over 4 and so on. Ultimately, we'll get that this is less than or equals to a1 over 2 to the t over 2, but a1 is just a. Yeah, so it's also clear from the algorithm that at is always going to be greater than or equals to 1. Why? Because if, okay, so bt is going to be greater than, bt is going to be less than or equal to at. So if at is not at least 1, at and bt are both 0. But in that case, bt minus 1 would have been 0, and we would have stopped at the t minus 1 iteration itself, right? So the fact that the t iteration was executed means that at is at least 1. So this means that 1 is less than or equals to a over 2 to the 2, which implies. So now we can take log base 2 on both sides, and since log is an increasing function, or rather a non-decreasing function, we get that log 2 base 2 is 1, so we get, oh, this is less than this. T is less than equals to 2 times. Yeah, so this is a better running time on the this is a better upper bound on the running time of uh, Euclid's algorithm. So we have shown that we require at most order log a many iterations. And if you go back to the algorithm, each iteration, the amount of computation happening is so this computation per iteration takes constant time, right? So the overall running time of Euclid algorithm is also order log a based. Yeah, so it's very efficient. Now let's look at the next problem. This is the next problem asks us to construct a zero knowledge protocol for every language in NP. Recall that in the class we saw how to construct a zero knowledge protocol for one NP complete language, right? That was the three colorable language. So what we'll do in this problem is that we will use that protocol to construct a zero knowledge protocol for every language in NP. So let's see how we can do that. Okay, so what we'll do is we'll use the Cook-Levin theorem. So the Cook-Levin theorem states that. So recall that the Cook-Levin theorem states that 3 set is NP complete, right? That is, it gives us a reduction from every language in NP to 3 set. But we also know that 3 colorable is NP complete. So there is a reduction from 3 set to 3 colorable. So by using Cook-Levin theorem and that reduction, from 3 set to 3 colorable implies that there exists, or rather, there exists a function f from 0, comma 1 to 0, comma 1 star such that x is an L if and only if f of x is in 3 colorable. And this also f can be computed rather with f of x. And this immediately suggests how we can give a zero knowledge protocol for the language L using the zero knowledge protocol for 3 colorable. So we have a prover with access to x, we have a verifier with access to x, both compute f of x. Now, f of x is in 3 colorable if and only if x is in L. So to convince the verifier that x is in L, all the prover has to do is to convince the verifier that f of x is in 3 colorable, right? But we know of a zero knowledge proof for that, right? So now what we are going to do is use the ZK proof to f of x is in 3 colorable. And since this we can do it in zero knowledge fashion, we can convince the verifier that f of x is in 3 colorable in zero knowledge fashion, and therefore we can convince the verifier that x is in L in zero knowledge fashion. Yeah, so using Cook-Levin theorem in that one zero knowledge protocol, we can come up with a zero knowledge protocol for all languages in NP. So now let's look at the next problem. So recall that we have seen commitment schemes in the class. In particular, we constructed commitment schemes in two settings. One when one when we are in the random oracle model, and one uh, when we weren't in the random oracle model, we were in the standard model, but we use the D-log assumption, right? So we constructed commitment scheme either based on the random oracle assumption or the D-log assumption. In this question, what we'll do is we'll construct a bit commitment scheme. That is a scheme that allows us to commit one bit, 0 or 1, using another assumption. And what we'll assume is that a one-way permutation or OWP exists. So the question is to construct a bit commitment scheme using a one-way permutation. So let's see how we can do this. So let f from yeah, it can be anything. Let me make it up. Since it's a one-way permutation, I can assume that the range and codomain, sorry, the domain and codomain are the same. As would be a one-way permutation. And so recall that we saw when we were looking at private key primitives, we saw that for every one-way function, you have a one-way, you have a hardcore predicate. Similarly, for every one-way permutation, you also have a hardcore predicate. And let's see. So a hardcore predicate is something that's difficult to compute given f of x, but easy to compute given x, right? That was the definition of hardcore predicate. So here's the commitment scheme. You have a sender and you have a receiver. Sender wants to commit. So to commit to B, what the sender does is it fits an X uniformly at random from 0, 1 to Pn and sends the commitment C is equal to C0, C1, where C0 is equal to f of x and C1 is P, and to open the commitment, what the sender does is it sends uh, X and B. And what does the receiver do? The receiver does the following. If C0 is equal to f of x and C1 is equal to B, except if and only if both are true. Okay, so this is the commitment scheme. Now let's prove its hiding and binding properties. So what we'll do is the following. We'll show that if there exists an adversary A which can break the hiding property, then there exists an adversary A subscript HC which can break the hardcore predicate. That is, which can compute the hardcore predicate just given f of x, which would violate the assumption that it's hardcore predicate. So that would imply that no such A can exist. So okay, so over here we are going to play the hardcore game, and okay, over here we are going to play the hardcore predicate game, and over here we are going to play the hiding game. So in this case, and AHC is supposed to reply with HC of X. What does AHC do? It forwards this commitment. It forwards this commitment. So yeah, let me. That should be is big uniform. Yes, which I don't think we need to pick the uniform return above 0, comma 1. We can probably also work with b equals 0, but let me do it with this. Now A is going to reply with B prime, where B prime is the opening of this commitment, right? And what does A do? It checks if yes, then set B double prime equals to 0, name 1, and reply 1. So the guess of A at C for the hardcore predicate at C of X is B double prime. So let's see why this works. So if B prime is the opening, uh, B prime must be B, right? Yeah, so if P is not equals to B prime, then HC has to be 1, right? So what this tells us is that the probability of success of A at C, okay, so is half. This commitment scheme with half less negligible probability or less than half less negligible probability, which is fine because anyways A could have guessed with probability, guess the correct answer with probability half, right? Because the commitment is to a bit, you can guess the correct bit with probability half. So this is good enough. This means that A, this scheme has hiding. Now let's look at binding. So suppose that B prime and B are both openings, or rather, since it's just a bit commitment scheme, of uh, C is equal to f of x, comma. Okay, let's say this is just an opening of it's let's say uh, C0 comma C1 where C0. Okay, yeah. So let's say that this is the opening of both. So let's say the commitment C is equal to C0 comma C1 can be open to both 0 and 1, right? So to open to 0, since x and 0 for some x in 0 comma 1 to the n and to open to 1 since x prime comma 1 for some x prime and 0. Okay, but then C0 is equal to f of x equals to f of x prime. But since so f is a one-way permutation, therefore it's a permutation. This implies as C1 is equal to 0 XORed with HC of x is equal to 1 XORed with HC of x. And this implies that 0 equals to 1, which is a contradiction. Yeah, so this means that you cannot open a commitment, any commitment to both 0 and 1. So the commitment also has binding. In fact, the binding is unconditional. The hiding was computational. Because, yeah, computationally unbounded adversary can break the one-way permutation. Yeah, so this was a commitment scheme based on one-way permutation. So now we have seen a commitment scheme based on uh, D-log and a private key assumption one-way permutation. So that's all the problems that's for today. Thank you.